So this is the outline of chapter 30, induction and inductance. So we will talk about Faraday's law here, Lenz's law, induction, and then induced E field, and then inductor and inductance. So most of you are ECE students, so you should have learned it in circuit analysis. You know what is L, and then yeah. And then we'll talk about self-induction, RL circuits, and energy stored there in the magnetic field, and then mutual inductance. Mutual inductance is somehow like a transformer. So here we talk about the Faraday's law, and then let's take a look at this first experiment. So as you can see here, there's a hand holding a magnetic bar, and then here is another voltmeter. So actually, this is a ammeter. So it says a conducting loop is connected to a sensitive ammeter. So this is the ammeter. Sensitive means it can sense some small current. Ammeter is used to sense the current. So sensitive means it can sense some small current. Yeah. Okay, so because there is no battery or other source of EMF induced, EMF is the long term is called electromotive force. Electromotive force. Force. This EMF, electromotive force. 中文叫做电动势electromotive force. You can somehow regard it as a battery, something like that. A voltage difference is somehow like a electromotive force. So there is no current in the circuit. There's no battery here, so there is no circuit. Yeah. So however, if we move a bar magnet toward the loop, so this hand holding the magnetic bar and then move toward this loop, and if you still remember, I hope you still remember this loop. If there is some current going through this loop, then it is actually a magnetic dipole. If you still remember, a magnetic dipole. And the magnetic dipole is defined as mu times NIA. Sorry, I forgot to call it. Okay, so yeah, so this is a magnetic dipole. If there is some current going through it, so it is a magnetic dipole, and the magnetic dipole moment is mu equals NIA. N is the number of turn, I is the current, A is the cross-section area. So actually this is a circle. And so it says if we move a bar magnet toward the loop, a current suddenly appears in the circuit. The current disappears when the magnet stops moving. So it depends on the motion of this magnet bar. If we then move the magnet away, the current again suddenly appears, but now in the opposite direction. So if we move this magnet bar towards this this loop, then there will be a sudden current. If you just hold the magnet bar near the loop, then there will be no current. If you move this magnet bar away, then there will be a suddenly current again, but in the opposite direction. So this is the phenomenon that we observe in this experiment here. So for the yeah, so it's continues to say a current appears only if there is a relative motion. Relative motion means the motion between this magnet bar and this loop. So between the loop and the magnet bar, one must move relative to the other, which means that if you just hold the magnet bar there and then move this loop toward the magnet bar, then there will be a sudden current there. So the current disappears when the relative motion between them cease. Cease means stop. Cease means stop. Stop. So fast motion of magnet produce greater current. If this motion move faster, then the current will be larger. So it is different from before. Before, if we have a charge, then it will generate E field, and if the voltage is large, then the current will be large, which follows the Ohm's law. But here, the current itself related to the motion. So if the magnet's north pole towards the loop causes, say, clockwise current, then moving the north pole away causes counterclockwise current. And actually, the direction of the motion also influence the direction of the current. So moving the south pole towards or away the loop will cause current, but in reverse direction from the north pole. So this motion of this magnet bar will influence the current direction. Also, north pole or south pole will also influence the direction of the current. So here you can see another experiment. It is similar. You can still see this ammeter and this loop, but the magnet bar changed to another setup. You can see another loop here. Of course, these two loops doesn't touch each other. And here you can see a resistor and a battery and a switch here. So if the switch is closed, then there will be a current going through this loop. And in the previous chapter, you know that this loop with a current is equivalent to a magnet bar. So for the magnetic field point of view, this one and this one is equivalent to each other. So for this experiment, you will use the apparatus 仪器 with the two conducting loop close to each other but not touching. If we close switch S to turn on a current in the right-hand loop, the meter suddenly and briefly register current and induce current in the left-hand loop. Yeah. So the phenomenon are similar. So if you close the switch, then it will become a magnetic dipole, and it will generate magnetic field. So if you move this setup towards this ammeter loop, then there will be a certain current. So if the switch remains closed, no further current is observed. Oh, sorry, not this case. It actually says you doesn't need to move this one. You just need to switch on or switch off this switch. So if it is open, then there will be no current. And if you just close the switch, then there will be current. Then there will be a sudden current on this left-hand side loop. It says if the switch remain closed, then there will be no further current. Then if we open the switch again, then another sudden current briefly introduce a current, but in the opposite direction. So this switch on action, similar to moving this magnet bar close and away from this loop. So we get an induced current only when the current in the right-hand side loop is changing. Changing is very important. Changing, which means the magnetic field, or actually the magnetic flux going through this loop, is changing. So as this case, you can imagine when the region is close to this magnet bar, the magnetic field is stronger. For this side, the magnetic field, or the magnetic field here is weaker. So yeah. So actually, if you just move this bar towards this loop, the magnetic field crossing this loop is changing, is also changing. So as this case. And the induced EMF in this experiment apparatus caused when something changes. But what is that something? Faraday's no. Okay, so it says Faraday realized an EMF and a current can be induced in a loop, as in our two experiments, by changing the amount of magnetic field passing through the loop, which is actually the magnetic flux. So he further realized the amount of magnetic field can be visualized in terms of magnetic field lines passing through the loop. So he defined the magnetic flux here by B, which is B dot dA, the integration. This is not a closed surface, so we don't have a circle here. This is not called closed surface. The surface is nothing but this area bounded by the loop. So the magnetic flux phi B through the area A in a magnetic field B is defined as this one. The integral is taken over the area. The SI unit is called Weber for the magnetic flux, which is actually Tesla times meter square, because B is the SI unit for B is Tesla. The SI unit for area is meter square. So this is T meter square, and which is defined as Weber here. So if B is perpendicular to the area, so this integration is nothing but a multiplication, B times A. So nothing special, similar to the one we learned for the electric field, the electric flux, something like that. Okay, so here we talk about the Faraday's law of induction. Faraday's law of induction. So the magnitude of the EMF E induced in a conducting loop is equal to the rate at which the magnetic flux phi B through the loop change with time. Just now we already mentioned that if something is changing, then there will be a sudden current. And Faraday tells you that this current is actually related to the rate of change to the magnetic flux. And so here is the statement for the Faraday's law with the notion of magnetic flux. I think should be motion or notion. we can say Faraday's law in a more maybe a notation or something like in a more quantitative and useful way. So it says E is the EMF. And then phi B is the magnetic flux. And then we take the derivative of the magnetic flux with respect to time, and then with a minus sign, which will be the induced EMF. So E is the induced EMF. The induced EMF to the opposite of the flux change, and the minus sign indicate the opposite opposition. This minus sign is referred to as Lenz's law. So only this sign, we already call it the Lenz's law, which means you can say you use the Lenz's law to determine the direction of the induced EMF or induced current. But actually, this is actually the Faraday's law. Or if if there are n turns for the coil, then we multiply it by n. So nothing special here. Okay, so yeah. So let's take a look at this sample problem 30.01. So it says a long solenoid S has 220 turns per centimeter and carries a current I. Its diameter D. Yeah, which means the big one. The big one. Okay, as it is, as the center, we place 130 turn closely packed coil C. So this one is C. The big one is S. Closely packed coil C of diameter small d, the current in the solenoid is reduced to zero at a steady rate in 25 milliseconds, which which means that the current starts at 1.5 ampere and it reduces to zero in 25 milliseconds. What is the magnitude of the EMF that is induced in coil C while the current in the solenoid is changing? Yeah. So so now we need to consider the magnetic flux phi B, which is B times A, because we assume the magnetic field is constant, is uniform. And in chapter 29, if you still remember the magnetic field generated by the solenoid is mu naught I times small n, and then A. N is the number of turn per unit length. Number of turn per unit length. Okay, so here mu naught is 4 pi times 10 to minus 7, and then the current is 1.5A, and then times turn is 220, but per centimeter. So we need to convert it to 220 times 100. So we have two more zero at the end. Turns per meter, like this. Okay, so this is 22,000. And then A will be this one, pi r squared. So pi r is 0.032 over 2 quantity square. Okay. Oh, sorry. We should use that one. We should use this one, because we need to consider the magnetic flux here. Phi B refer to here. Yeah, phi B refer to here, because we are considering the current generated by the induced current generated in this coil C. So we should use 0.021 here. Okay, so this value should be 1.44 times 10 to minus 5th Weber. Okay, so this is the magnetic flux, and we actually need to calculate the d phi b dt, which is actually minus 1.44 times 10 to minus 5th, reduced to zero in 25 milliseconds. So over 25 times 10 to minus third power, which is minus 5.76 times 10 to minus 7 Weber per second. So finally, we can get the induced EMF E to be minus N d phi B dt, which is here 130 turn minus 130 times d phi B dt is minus 5.76 times 10 to minus 4th power. which is 75 millivolt. So this is not so difficult. We only need to use this 30.5 to calculate the EMF. Just plug in the value, and it will be fine. And so far, any questions? If you have questions, please leave in the comments or leave in the chat. And next, we will consider the direction, which is not so trivial. And so here we talk about the Lenz's law, and induced current has a direction such that the magnetic field due to this induced current opposites the change in the magnetic flux that induces the current. So the induced EMF has the same direction as the induced current. So the Lenz's law at work, as the magnet is moved towards the loop, the current is induced in the loop. So previously, we already mentioned the two experiments. It has something like that. The current produces its own magnetic field. So here, let's talk about how to determine the direction of the induced current. So there are 12. So we look at it one by one. So actually we have 4. 1, 2, 3, 4, A, B, C, D. So at the very beginning, let's start it here. So B. Induced B. So here, the direction of the current induced in a loop is such that the current magnitude, current magnetic field BIND opposite the change to the magnetic field B inducing I. So here, B is the external field. B is the external field generated by something else, maybe a magnetic bar or maybe a magnetic dipole. So suppose we have this B pointing downward, and then the loop is something like that. And if we increase the external field B, so it starts from here, become larger. In this case, B induced will point to the opposite side. It is somehow like it generates some B field, counteract this changing, because this magnetic field is changing from this one to a larger value. And then it will try to generate some B field, point to the opposite side. And in that case, using the right-hand rule, you use your thumb, follow the direction of the B induced, and then this finger will point to the direction of the induced current. So this is the direction of the EMF and also the direction of the induced current, like this. Okay, so it basically tells you this case. And for this case, if originally the B field is pointing downward and decreasing the external B field like this. So it's changed from the green one to the blue one. So this loop will try to generate a B field pointing downward to counteract this change, because this is the delta B. The delta B is pointing upward. So this B induced will pointing downward. For this one, delta B is pointing downward. So B induced will pointing upward, like this. So so it will generate a B induced pointing downward, and using the right hand rule, we will have the current. This one is something like clockwise. So this is the front, this is the back. So this is clockwise. If you just see it on the top, from the top. This is the second case, and then the third case. So the B field is pointing upward, and it start to increase. So it becomes this one. So the delta B is something like this, pointing upward. So B induced will be pointing downward, which means the opposite direction to this one. So using the right hand rule, the current is clockwise. And then for the fourth case, B is originally pointing upward, and we try to decrease the external B field. So the B field becomes this one, and then this is delta B. Pointing downward. So B induced will pointing upward to counteract this change. So B induced pointing upward, and then using the right hand rule, the induced current is counterclockwise. Okay, so up till now, we know that this is B induced pointing upward. This is B induced pointing downward. B induced pointing downward. B induced pointing upward. So sometimes they point to the opposite direction. Sometimes they point to the same direction. So it doesn't necessarily, it does not related to the direction of the B field, but it related to the change of the B field. So this is not so trivial at the very beginning, but yeah, it is not difficult at all. So this is called the Lenz's law to determine the direction, of the induced current. And here is a sample problem 3002. So it says a conducting loop consisting of a half circle of radius r, so this small r, and 3 strict sections. So these 3 strict sections. The half circle lie in the uniform magnetic field. So above this dotted line, there is a uniform magnetic field directly out of the page. So this is a dot, so it is out of the page. The field magnitude is given by this expression, B equals to a function of time, which means this magnetic field is changing with respect to time, with B in Tesla and T in second. The ideal battery with EMF, EBAT, this is EBAT, 2 volt is connected to the loop. The resistance of the loop is 2 ohm. So there will be a 1A current. So what are the magnitude and direction of the EMF induced around the loop by field at T equals 10 seconds? Okay, so now we consider the magnitude of the induced EMF, which is d phi b dt. So originally, the Faraday's law, we don't have this absolute value, and we have a negative sign here. But actually, we can determine the magnitude first, and then determine the direction using the Lenz's law. So we can only consider the magnitude, the absolute value here, to reduce the difficulty, something like that. Yeah, so d phi b dt, the phi b is nothing but b times a, because the b is uniform over this region. And a is a constant, so we can just put it outside. So we have a times dB dt. So next, A. A is this area of the half circle. So it is pi r squared over 2. And then B. B is this one. So we have 4t squared plus 2t plus 3, like this. So we have pi. R is 0.2 meter. So 0.2 square and then over 2. So this one, the derivative of this polynomial is simple. So we have a 4t squared, take the derivative will be 8t. And then 2t, take the derivative will be 2. And then 3 is a constant, take the derivative will be 0. Like this. Okay, so yeah. So if we just find the magnitude of the EMF at t equals 10 seconds, we just need to plug in t equals 10 seconds. So EIND of t equals 10 seconds, like this, will be pi 0.2 square over 2, and then 8 times 10 plus 2. So this is 5.2 volts. And of course, we need to determine the direction. So we can see that this one is actually increasing with respect to time, because all the coefficients are positive. So which means if t is larger, the whole term b is larger, which means d phi b dt is larger than 0, or phi b is increasing. Phi b is increasing, which means that this phi b pointing out of the page is increasing. So the I induced should be, the B induced should be pointing into the page, because the external B field is pointing out of the page and increasing. So B induced should be pointing into the page due to the Lenz's law. And in that case, using the right hand rule, your thumb pointing into the page, your forefinger will be clockwise. So the direction, the induced current is clockwise. Okay. So we still have part B. What is the current in the loop at t equals 10 seconds? T equals 10 seconds. So just now we know that E induced is 5.2 volts, which means that this is the direction of the current, and also the E induced. So it is something like it is not so accurate, but you can regard it as it is like E induced is something like that. Although this E induced is distributed for the whole loop. Yeah, but sorry. So, not this case. Should be something like this. Yeah. Because E induced is in this direction, and actually this is the I induced. And if you just ignore ignore this part first. Then you will find the current. The current should be going in the opposite direction, in this direction. Because if you have this E battery and then this loop, we have a resistance there. This is 2 ohm. So this current should be pointed to that direction. So these two should cancel part of each other. In this case, the I should be, and actually the total I here will be E net out to be E induced minus E bet over the loop resistance 2, the loop resistance. So in this case, E induced is 5.2 volt, E battery is 2, so R is 2. So this value is 1.68. Yeah, so you can regard it as something like this. There is a battery in this direction, so that it will generate a current in this direction to cancel part of this one. Yeah. Okay, so far any questions? Okay, so we have another sample problem here. So the figure shows a rectangular loop wire immersed in a uniform and varying magnetic field B is perpendicular and directly into the page. So B is pointing into the page. The field magnitude is given by this expression. The loop has width W. W is the width, and the height is H. What are the magnitude and direction of the induced EMF around the loop at t equals 0.1 second? Okay, so the magnetic field B here is not uniform. It's not uniform. It related to the x-axis coordinate. So we have an x here. Okay, so we need to do some integration. So phi b will be the integration of b dot dA. And actually it is perpendicular to each other. So we have only b times dA integration. And b takes this expression. So we have a 4t square x square d. dA is actually this one. So dx is the width. dx is the width, and then times h will be dA. dA should be h times dx. H times dx. So which is the area of this rectangle. So we have dA to be h dx. Okay, so we have we should have the lower and upper bound. This is 0, and the width is 3 meters. So this is 3 meters. So here we should integrate from 0 to 3. Okay, so we have 4t square h So all these terms are constant with respect to x. So we have integration from 0 to 3 x squared dx. And of course, h is 2 meter here. H is 2 meter here. So it is actually 8t squared. And then this integration, x squared, the integration of x squared should be x cubed over 3. So we have a x cubed over 3, and then evaluate from 0 to 3, which should be 3 cubed over 3 minus 0 over 0 cubed over 3, which is 0. So this is nothing but, this is this is nothing but 9. 9 times a is 72 t squared. So this is 5b, and we can evaluate E equals, the absolute value of E is d5b dt. d5b dt, which is d dt 72 t squared. And take the derivative of t squared will be 2t. So it is altogether 144 t. And if we need to evaluate this induced EMF at t equals 0.1 second, so we have E of t equals 0.1 second will be 144 times 0.1, which is 14.4 volts. And here, the direction of the magnetic field. And also we can see that this one, x is positive, and if t is increasing, b should be increasing. So delta p and delta b is pointing into the page. So b induced should be pointing out of the page. In that case, using the right-hand rule, we can see the induced current should be counterclockwise. The induced current is counterclockwise. 逆时针，逆时针。And EMF. Any questions? If no question, let's take a 10 minutes break.